So for the two different types of simple harmonic oscillators that we're going to focus on in this class, there's a set of equations that describe their motion. So if we have linear simple harmonic oscillators that bounce back and forth along some line, the equations of motion for a linear simple harmonic oscillator are given on the left. If instead we have an angular simple harmonic oscillator that's going to swing back and forth through some angle about equilibrium, those equations of motions are given here on the right. Now, for either set, the important thing is that we know how to relate the displacement to the velocity to the acceleration. So whether you're talking about the linear simple harmonic oscillator or the angular simple harmonic oscillator, basically we know that we're going to take the derivative of this x equation to get the x component of the velocity. And then we're going to take the derivative of the x component of the velocity to get the x component of the acceleration. We can do the same thing with our angular simple harmonic oscillators, and so we can take the derivative of this equation for theta, the angular displacement, to get the angular velocity. So again here, because we're already using omega inside our cosine function for the angular frequency, the angular velocity, which we typically use with omega, we still are, it just happens to be a capital omega in this case. So you take the derivative of theta and you get the angular velocity. You take the derivative of the angular velocity, you get the angular acceleration. And so what you notice is a couple of things. One is for each of these, because they start with an amplitude times a cosine function, and that cosine function has a phase of omega t plus phi, that when you take its derivative, a couple things happen. One is the derivative of cosine is negative sine. And then also because you have to use your chain rule, you end up with this extra omega coming out. And so what you end up with is that you have a velocity function in either case that is negative omega, the amplitude, times now the sine of omega t plus phi. And again, that's true for either your linear simple harmonic oscillator or your angular simple harmonic oscillator. The only difference is here, the amplitude is some distance. Here, the amplitude is some angle. Again, we take the derivative again, and the derivative of sine is cosine. Again, we need to use the chain rule so that we end up pulling out a second omega, and so we end up with negative omega squared times the amplitude times now the cosine of omega t plus phi. And again, a cosine omega t plus phi, well, that was our expression for x. And so what I notice is that the x component of the acceleration is equal to negative omega squared times the displacement. And again, that's true for both my linear simple harmonic oscillator. It's also true for my angular simple harmonic oscillator. So with an angular simple harmonic oscillator, I have that the angular acceleration is equal to negative omega squared times the angular displacement. We'll talk a little bit more about this in the next video, but this relationship that relates the x component of the acceleration to the linear displacement or the angular acceleration to the angular displacement, this relationship defines simple harmonic motion. Now again, if we think about these three equations, we can figure out, well, since these are either cosine or sine functions, and the maximum value that sine or cosine can take is 1, then the maximum value that any of these expressions can have are given down here below. And so you'll notice that for my linear simple harmonic oscillator, the amplitude is just another way of saying, well, what is the maximum distance it's been displaced from equilibrium? Same is true for my angular simple harmonic oscillator. The amplitude is just the maximum angle that my angular simple harmonic oscillator was pulled away from equilibrium before you let it go. The maximum speed at which it's going to travel is omega times a. And again, that's true for both linear and angular simple harmonic oscillators. It's just my a is different. Here it's a maximum value of x, here it's a maximum value of theta. My maximum acceleration, again, in its magnitude is going to be omega squared times a. And so if I have a linear simple harmonic oscillator, this is omega squared times x max. If I have an angular simple harmonic oscillator, this is omega squared times theta max. So these are what are known as the equations of motion for simple harmonic motion. Now, since we know that we have sines and cosine curves, we know how those plot out. And so let's just think about sort of going through a full cycle. And it's easiest to deal with this for a spring and mass system. So we're going to choose to look at this with our linear simple harmonic oscillator, but it doesn't really matter, right? We'd get exactly the same thing if we were plotting this instead of in terms of linear variables. We're plotting this in terms of angular variables for an angular simple harmonic oscillator. And so what we've got here is we've got all three curves. So the blue is the displacement. That's my function x. Red is the velocity. So that's my x component of the velocity. The green curve is the acceleration. So I've plotted all three curves on top of each other so I can see what they're doing in time. So let's start by having my block out here at, in this case, positive amplitude. And so you'll notice that what that means is, sure enough, I'm at the maximum value for the displacement curve. I know at this, when it's at amplitude, that's the point it's stopping to turn around. So the speed here has to be 0. Sure enough, that's what's going on with my red curve. My red curve is crossing the axis, so its value is 0. And then the acceleration, again, it's at its maximum, but it's pointing back in the negative direction. So I have a displacement that is at its maximum positive value. At the same time, I have an acceleration that's at its maximum negative value. If I let my system continue to bounce, so it's going to get back to equilibrium. And again, here we're not worried about what the mass is. We're going to treat the mass as a point particle. So mostly I'm just going to, in terms of this graphic, think about what's going on with the distance the spring is being stretched or compressed. And so here I've come 1/4 of the way through my cycle. And so what I notice now is, well, I'm at equilibrium. So my position is 0. My mass is traveling with its maximum velocity in the negative direction. So again, it's moving as fast as it ever will. It's moving in the negative direction, and sure enough, that's what I see in the curve. It's at its maximum value. It's negative. Because it's back at equilibrium, the acceleration is 0. And again, that's exactly what I see with my acceleration curve. It is also crossing the axis here, so its value is also 0. If I let my mass keep moving, so it started at amplitude over here, I let it swing all the way over to amplitude over there. So now it's at its negative amplitude, so it's at the largest negative value it's ever going to have when it's gone halfway through the cycle. So this is 1/2 t. It's stopping to turn around. And sure enough, that's what I see with my velocity curve. The red curve showing me the velocity is, again, crossing the axis, so its value is 0. And its acceleration, the acceleration acting on the mass, is once again at its maximum because it's as far away from equilibrium as it's ever going to get, but now it points in the positive direction. So my acceleration curve is at its maximum positive value when my displacement curve is at its maximum negative value. Let it keep bouncing, and again it's going to go back through equilibrium. That'll take another 1/4 of the way through the period. So I've gone from where I've started to equilibrium to the other amplitude back to equilibrium. So now I'm 3/4 of the way through the period. Again, I'm back at 0. So sure enough, my blue curve is crossing the axis. I'm moving with the maximum velocity in the positive direction. That's what my red curve shows me. And again, because I'm at equilibrium, I know that my acceleration is 0. And again, my green curve is crossing the axis to confirm that. Let it go back to where it started. And again, now I've gone all the way through my period. And I'm back in terms of being at a maximum positive displacement on the blue curve, 0 on the red curve because the velocity is 0, it's stopping to turn around, and at a maximum value, but in the negative direction for the acceleration. So these are the equations of motion. These are how they plot out. These are how they relate to each other. So the phase shift between the displacement curve and the velocity curve is they are 90 degrees out of phase with each other. When one of them is at a maximum, the other one's at 0. The phase shift between the velocity and the acceleration is they're 180 degrees out of phase with each other. They're at 0 at the same time. They're at maximum values at the same time, but one of them is going to be at a positive maximum value while the other one's at a negative maximum value. And so this comes from the fact that, again, these are both cosine curves, but the acceleration curve has a negative sign sitting out in front. The displacement curve doesn't. The velocity curve is a sine curve, and so that's where the 90 degrees out of phase comes from.